Hello and welcome everyone. Very good morning to all of you, and welcome to the second session of the Responsible Artificial Intelligence course. Today we have our speaker, Dr. Bhushan Garware, whom we have met for the first session also. And today he is going to talk about interpretable and explainable AI, generating explanations for structured data. Over to you, Dr. Bhushan.
Thanks, Prachi. Hello and good morning, everyone. Hope my screen is visible.
Yes, we can see your screen.
Yes, thank you. Uh, so today, uh, in this course of responsible artificial intelligence, today we will be at lecture number 2, that is interpretable and explainable AI part 1. When I call it as a part 1, I will be covering basics of explainability, how to generate explanations, what is the thought process. And this session, we are scoping only to the structured data, mostly a tabular data that we work. And then we have another lecture number 3, where we will be focused on generating explanations on complex models like uh, NLP models or imaging models. So basically handling unstructured data that we will be covering into the third session. So the scope for today's session is to understand what is the need of explainability, how that is generated, and there would be an hands-on session as well. So I believe everyone has received an email from Prachi, and I have shared some set of notebooks. So we will be needing those notebooks when we will be doing hands-on. So I'll not only teach you the concept, we will actually apply it on some kind of a data sets, and we will actually feel that how those explanations are being generated. Now, for the sake of simplicity, I have taken only one data set, that is a PIMA Indian diabetic data set, a typical classification problem. But the method that I'm going to teach, those are model agnostic. So what I want is, after this session, no matter in whatever domain that you people are working on, take these notebooks and replace it with your piece of code. Okay, so that you can start using this. So that is the end purpose of this session. So I'm gonna cover the theory, I'll tell you their importance, but the real achievement of this session would be if you take these learnings and apply it in your domain and start using it into your day-to-day activity. So with that, uh, I hope every one of you have received an email. So there is a folder called XAI Notebooks. I would request you to download that and keep it ready on your desktops. Okay. And I'll tell you how to use those notebooks, and we will execute those notebooks together. With that, let me get started with today's session. Again, the views, thoughts, opinions expressed in this presentation belong solely to the presenter and not necessary to be the presenter's employer, organization, committee, or other group of individuals. When we started our first lecture on key pillars of responsible AI, one of the limitations of existing or deploying black box models that we discuss is this. When someone asks for a credit line increase, you generate a features and then you query your AI system, and your AI system returns your score, which is interpreted by somebody saying that score is zero point 0.3. There could be a set threshold, say 0.7. So your 0.3 is much lesser than your 0.7, and that's why you are saying that the request is denied. And then we discuss about what are the implications of deploying such black box models. You are having unhappy customers and they don't know that why not, or how I'm getting these kind of a decisions. Then we say that, in order to have a responsible deployment of AI, these are the 5 pillars: interpretable and explainable AI, secure and private AI, compliance and ethical AI, reproducible AI, and accessible AI. So today we're gonna double click on the first pillar of responsible AI, and that is interpretable and explainable AI. So we discussed that why there is a need of that, and this is a typical structure of current AI systems. You have a training data, there is an model building process which happens in isolations. The team of experts like data science experts and data scientists, they work on the data and give you a learned function. So that learned function is actually deployed in the systems which are used by end users, which may or may not be familiar with data science. So end users, they always struggle to get the answers of the question like, why did AI do that? Why not something else? When did AI succeed? When do it fail? When can I trust AI? And how can I correct the errors? So end users, they will not be able to get answers if your learn function is a black box to them. And then I gave some very interesting examples. I'll not spend much time just to bring you into a same page. If in case somebody missed the first lecture, I gave you an example saying that your AI systems are not only wrong sometimes, they not only produce wrong results, but they are very confident about their wrong results. And the example I gave is for this particular image, your model says that this is a guitar with a confidence of 98.90. But for this image, it also says that this is a guitar. And in this case, the confidence is much higher. So I told you, you cannot just set a threshold and say that, you know, my AI model is accurate or I can trust that. So that's why we needed explainability aspects along with the decisions. Then I gave very interesting example. I hope you remember that this was a Husky and Wolf classifier, and we say that on paper the accuracy was amazing, but what you ended with learning is you designed a snow detector, right? So that's why it's very important to understand what your algorithm has really learned in order to make the decisions. And then gave some examples in healthcare, and we discussed some examples into word analogy like man as to doctor and woman as to nurse, right? So today what we are going to do is, I told you the standard procedure of designing AI model is you want to build a model, you have a training data, and initially the goal was only to reduce your error, so no matter what happens, I have to reduce my error, and then I'll say that my model is accurate. But in case of explainable AI, the goal is not just to reduce an error. The goal is to make sure that model has learned right features. And how can we figure out that model has learned the right features? You have to have a human in loop, and this is an expert. This may not be necessarily a data scientist. This can be someone from a domain expert. If you are building a model in the healthcare domain, as a data scientist, your job is to minimize an error. You'll choose right algorithm, you'll do right feature engineering, fine tuning, and you will say that my model is accurate. But what you have learned should be shown to an human expert in order to convince him the model has learned the right features. And for that reason, what you need is explanation interface. So today's session is dedicated to generate this interface along with your AI model, right? So when we say that we will go from AI to XAI, from black box to transparent model, what we have to give is an internal working of this model, right? So let's get started for the today's session with that background. So first of all, let's try to understand what do you mean by interpretability. So if you see this in this lecture, we have used these terms called interpretability and explainability, right? So let's split that. So Tom Miller, I hope everybody knows. So what he says that, interpretability is a degree to which a human can understand the cause of a decision. So simple definition. When you say that my model is interpretable, you should be able to find why a particular decision is made by this model. When my model is saying, suppose you have designed a diabetes prediction model, when model is saying that this person has high chances of having diabetes, you should be able to tell that why, what is the cause behind taking that decision. Okay, so now when we say that, okay, interpretability is a good to have because you will be able to generate, or you will be able to provide justification for the decisions made by your model. But now, do we all can we make a claim that all my machine learning models are black box models? Not really. So there are some machine learning models which are inherently interpretable. So what do you mean by inherently interpretable? The models that generate explanations in the process of decision making or while being trained. So the models are designed in such a way that when you make a decisions, you get explanations as a byproduct. Okay, so models are designed to include explanations embedded as a part of their architectures. And can you make some of those? The very first algorithm that we learn in any machine learning course is a linear regression model, right? And you understand that how simple it is. What you have to find is it's a straight line, and if there are multiple variables, you have to find the coefficient of that, right? So when you say that the model is learned, what you are actually learning are the coefficients for each variable, right? So what the theory says that interpretable models, if you are able to understand the cause of a decision, then you can call it as an interpretable model. But some of the machine learning models are inherently interpretable. Okay, and what are the names of those models? Linear regression, logistic regression, decision trees. Now let me tell you why I'm calling these kind of models are inherently explainable models. Okay, let's take this example. Suppose I'm designing a decision tree algorithm, and this is my attribute 1, attribute 2, attribute 3. Once a model is trained, you can easily interpret the decision. Okay, this is how a decision tree is built. If my at, attribute 1 is greater than on something, if it is yes, then you will see a return saying that answer is positive. If it is no, you see for the next attribute, and if it is yes, and if it is no. So once a model is trained and once a decision is made, can you backtrack and you can actually justify your decisions? Yes, you can, right? So a structure of decision tree, because of its simplicity, we call that decision tree kind of a models are inherently explainable. And whenever a decision made, you can actually say that what is the cause of this decision, why my model is saying one and why my model is saying it negative. Are you with me? And that's how. So while training, you never thought of this, but once a model is trained and once a decision is made, if I ask you to justify, you will be able to do it from the decision tree models, right? Let's talk about linear regression model. Okay, so this is your target variable that you try to predict by using a linear regression model, right? Now what you have is your x1 is your feature, x2, x3, x4, x5, xn. These are your n number of features, right? What you have to do is this is beta 0, beta 1, beta 2, beta n. These are the coefficients for your features. And what you say is my target variable y is a linear combination of my features. When you start training your algorithms, the coefficient beta 0, beta 1, beta n are unknowns, right? So you start with a random value of coefficients in your first iteration. Then you have a forward pass. Then there would be some predicted value y cap, which must be very far from what actually you wanted. That is a target value. So you find the difference between them, and then you go back and then you change the coefficients beta 0, beta 1, and beta n. You keep on doing that till the point you reach when your y cap and y target are exactly similar. And then you say that my model is trained. But the beauty is, the moment your model is trained, the values of beta 0, beta 1, beta n are freezed, right? And that's why once you have the knowledge of what are my coefficients, you are able to justify your decisions also, right? So when you say that my linear regression model is predicting the cost of the house as $300. So if the cost of the house is $300, you can justify saying that because my x1 is so high, because my x2 is so low, and my xn is medium, and their corresponding coefficients, you can say that my model is putting huge importance for x1, little bit importance on x2, little bit more importance on x3. And what are those importance? Those importance are your weights. And you can say that I'm not I'm not worried about whether that the prediction is accurate or not accurate. That depends on how good you find the coefficients. But once the coefficients are freeze, you will be able to generate the justifications for that. And that's why it is called as the simple models that we learned in our theory called decision tree, linear regression, logistic regressions. These are inherently explainable models. Okay, now there is a question for you participants. If a decision tree is a inherently explainable model, you can give me the ping on chat. Is the random forest inherently explainable model? Random forest classifier. I'm telling you decision tree is inherently explainable. Can you tell me if random forest is inherently explainable or not? Any answers? I'm getting a lot of no's. No, no, no. Random forest, no. Okay. Not inherently explainable. Okay. Now, can you tell me why random forest is not inherently explainable? In the back of a random forest, there is a decision tree, right? And the basic building block is explainable. But why then random forest is not explainable? Okay, because of its randomness ensemble of lot of decision trees. Yes. So you're right. So, I can say that my random forest classifier has hundreds of trees in the back. And because of this randomness, which features got split, which attributes got fetched, what is the length, max depth of the tree. There are too many things come into the picture, and it would be very difficult for you to justify for one particular sample why the decision of my model is good. So here you start understanding that the movement. But can you comment on accuracy of random forest classifier if you have done some of an hands-on? Tell me really, do you use a single decision tree in your experimentation, or you almost prefer random forest to get the better accuracy on the given data? Any questions? I'm getting a questions that it is more accurate, highly accurate. That's what a random forest is better. Okay. So now what people are claiming that, hey, Bhushan, we learn decision tree in the theory, but when we try to use it, what we use is a random forest, because what it gives us is a better accuracy compared to a simple decision tree, right? So I take your point, even I do that, but let's see what happens of that random tree. So this is the diagram, and then I'll say that why even you wait till random forest. You can still extend this to deep learning and neural networks and other difficult models, right? So this is the basis of need for explainable AI. Need for explainable AI. Why there is another branch and active research happening. This diagram will tell you. And at the end of this session, I'll open up a very interesting discussion for you as well. So what it says that there is a performance and interpretability trade-off. What it says that on an x-axis, you have interpretability matrix, and on a y-axis, you have a learning performance. Okay, so let's take a very simple algorithm called logistic regression. Now, logistic regression is what we learned in our theory, is a simple linear regression covered under a sigmoid function, right? And we have seen in the previous tree that you can justify the decision made by the logistic regression by saying that what are my learned coefficients. So logistic regression is highly interpretable model. But what is the limitation of logistic regression? The limitation of logistic regression is a simple linear classifier. You know that real life data is not linearly classifiable. It's a complex data, but what logistic regression can do is drawing a straight line on the top of it. Because of that, you will see that the learning performance of this model, is very low. So on this graph, I put that logistic regression here, right? Now, which next algorithm you learned in the theory? Now you can say that, hey, I don't have to stick to the uh, simple straight line for classification. I can have a non-linear boundary, so then I can use a decision tree. Decision tree is still a good interpretable model. So on x-axis, you will see that yes, it has a better interpretability compared to logistic regression. More performance compared to logistic regression, but you will see that still the learning performance is not very impressive. It is very good interpretable model. And then you learn the complex model, saying that then you can use for Bayesian belief network, you can use support vector machines, you can use random forest. So what random forest will do is it will boost your accuracy. So the learning performance is really high. But the time you achieve a very good learning performance, what you are losing, here is interpretability, right? So the decision tree has this much interpretable, but when you use random forest, you will lose on interpretability access. But what you got is a very good accuracy, right? Then why to stop here? What else you use? You also use deep learning and neural networks. So as per the theory suggests, you can learn as much complex function as you want. You can have a deep neural network, lot of hidden layers, very interesting techniques, and you can achieve the best accuracy that you want. But when you achieve the best level of accuracy here, what you lose in terms of interpretability, and you end up designing a black box model. And as I told you, nobody is accepting black box models. So this is the trade-off. You cannot have both. You will either have interpretability or you can either have accuracy. You cannot have both. And the moment there is a trade-off, there opens a lot of research opportunities for you. What is the demand? What is the need from industry? The need from industry is this. Industry says, no matter what kind of a model that you have used in the back, I want highly interpretable and explainable model. I'm not ready to lose on accuracy. Nobody likes to use less accurate model, but also we don't want to lose on interpretability also. And where we want to go it this. Take a very high accurate model, very complex model, and make it explainable. Okay, so that's the difference. It is not inherently interpretable like logistic regression or decision tree, but we will say that, okay, if you are not inherently interpretable, I will make you explainable. And how can I make you explainable is what we're going to learn in this session. Okay, so far so good. So everybody clear on what are we going to do? We're going to take very complex models from here and we will increase their explainability. Okay, so this is how it's called as an explainable AI. Okay, so let's move on. So what is the goal? And we call it, if your model is not inherently explainable, it's a nature. If by default, if it is not interpretable like logistic regression or decision trees, what I'll do is I will generate post hoc interpretable model. This is how the focus of today's session, we call it as an explainable model. Those are not inherently interpretable, but we will generate post hoc explanations for that. What do you mean by post hoc interpretable method? They aim to explain the decision making of the black box model after they are trained. So once a model is trained, I will give you full freedom to use as much complex model as you want. Make sure that it is highly accurate so that your one purpose is served, and then I will help you to generate explanations for that. So what we used to do before, We used to do before that, take a data, train a black box model, generate the prediction, and give that to the end user. Now, what we will give you, once this black box model is ready, give that trained model to me and some sample data on which it is trained, and I will generate explanations for you. And for the end users, along with your predictions, I will also generate explanations. Got it? So the second route is an extra work that we will have to do for the models which are not inherently explainable. And I hope from the previous slide, you all are convinced that why we have to do this, because we cannot compromise on accuracy. We do not have inherently explainable models which are highly accurate, and nobody likes to have a less accurate model. So this is a bypass. I'm not saying that this is a solution to the problem. The real solution to the problem is like you come up with your own algorithm which is inherently explainable and accurate, which is a very difficult path. So what is a bypass to the solution? The bypass to the solution is, do whatever you are doing right now. I will generate post hoc explanations of your model. And that's whole game of explainable AI in this domain, right? So how it is done? So if I want to generate explanations, I will have an explanation method, and then there are different explanation methods, different theories are available based on how you want to generate explanations. So some explanation method are model specific. Okay, you give me a model, and for that particular model I will generate explanations. So those are called as a model specific explanations. And typically you will see that in deep learning and computer vision applications, you will see that the guided propagation, integrated gradient, smooth grad saliency, then grad cam, and whatever concept activation vector. So these are the different techniques that people have generated for a model specific explanations. And there is another side of generating explanation. It's called as a model agnostic. And this is a very elegant method. And I really love that, because I'm saying that I don't care what kind of a model that you used in the back, I can still generate explanations for you. And there are companies now who are coming up saying that what we do is explanation as a service. You bring your black box model to us, and we will, in return, we will give you explanations back. So another techniques which are getting a lot of popularity are model agnostic methods. So model agnostic, they don't care what kind of a machine learning model is used in the back, whether it's a logistic regression or it's a decision tree or is a neural network or it's an XGBoost. We don't care. For all the methods, the explanation strategy is the same. And then they are split into other two categories. One is called global explanation and another is called as a local explanations. So I'll tell you what is the difference between global explanations and local explanations. So global explanation is, once you train your model, they will generate an explanation on entire data set specific explanation, right? This model, when it is trained, gave importance to which features, what are their compositions, how their decisions change at a global level. So what do you mean by global level and local levels? And in local level, from your data set, you can actually choose an instance saying that for this, my first sample, can you justify the decision? For my second sample, can you justify the decision? For my third sample. So every single sample, you will have a different explanation for that single sample in your data. And that's why it is called as a local explanations. And global explanation is at a data set level, overall at a model level. If you want to generate an explanations, then that is called as a global explanations. So we will be following this path in the today's session, that we will be mostly working on model agnostic methods, because that is the area where a lot of popularity, I could see many publications, many applications, many services. And it is elegant also because it's not restricting you from what kind of a model that you have using. And then we'll see some of an examples into a global explanations and in the local explanations. So far what we did is we say that we will have a black box model, the same black box model that you want to do, but we will generate ad hoc explanations for you. While generating an explanations, we will be using model agnostic explanations, and those explanations would be at a global level and at a local level. So far, so good. And if you are, then let me move forward to an actual explanations method. Are you with me? All good? Just give me some feedback so that I can move forward with actual explanations. Okay, thank you. Sure. So let's move to the first method, that is a global explanation method. The, the method is called as a feature importance. And this is a very logical step. Whenever a model is trained, people are always interested to understand out of all my features, what are the important features my model has taken into the consideration while making the decisions. What are those important features, right? Because if those important features are not in line with the domain, you may not you may feel that there could be a bias in your data or your model has not learned the right features. So let me explain you with an example. Okay, so first of all, let's try to understand that what is this method is all about. Okay, so feature importance, which feature has biggest impact on model prediction? So it answers that, okay, out of my, suppose there are 100 features, so which are the most important features that my model considers while making the decision? Okay, there are several ways of finding important features and their answers based on the method. So one of the why I'm talking about this, one of the fastest, consistent and easy to understand method is a permutation importance. So what this method does is very simple. Just see there. What it does is, suppose this is an hypothetical data set that I'm having, and this is my target column Y, and I'm having three features called A, B, and C. So in order to calculate the importance of feature B, B is a column in my data. What it does is it randomly swaps different values in my this column. So this xb1 would be swapped by something else. So it randomly changes the values into the xb column. Okay, from its own value. So maybe xb6 become xb1 and xb1 become xb5. So these are the random perturbation that it does within my column xb, keeping my all other columns constant. Okay, so please try to understand the intuition behind this method. What is saying that, okay, if my xa column, this value is same and this value is same, and I know what is the right answer when xa and xc is this, but when xb1 is changed, is there any change in my target column? So by keeping xa1 and xc1 constant, if my xb1 values changes by a small value, and if because of that, if my y1 is changing, that means my model is having high importance for xb feature, because by making a small alteration to this, my target is changing. I'm keeping column C value constant, I'm keeping column A value constant, and what I'm changing is the value of column B by its random sampling, random permutation across its values. So what it says that because of doing this, if the answer is changing, what I learned from this is the B column is very sensitive. You are not allowed a small changes in a B column is having a huge impact on my target column. Are you with me? So by this way, you do this one by one to the all the columns that you have, right? And then you will figure out that, oh my God, XB is the most important feature, looks like, because when I make changes to XB, my output is changing. When I make changes to XA, keeping XB constant, yes, there is a change, but change is not as big as I see in XB. So maybe A column could be of a less importance compared to B column, but the B column has the most importance. So this is done one by one on every column, and then you figure out that how much is a change in my target variable by making small changes into this value. So that gives me the importance plot. Right now, again, I have explained you in a simple way here, but you don't have to do it manually. There are awesome Python libraries available for you. Okay, so how to do it on your real life data? Let me switch to the IPython notebook, and let's do it together on a simple data. So there is a library called ELI5. Anybody knows what is the full form of ELI5? Put it into the chat without Googling. And meanwhile, let me open my IPython notebooks. You people also have notebooks with you. Let's do it together and let's see the outcome. So I have shared a folder. I think you have that folder with you also. That is XAI notebooks, right? So open that notebook. I hope you have uh, Anaconda installed, or uh, whatever tool that you use to run Python. I'm having Anaconda with me. So go to that folder and open Anaconda. Meanwhile, if you know what is the full form of ELI file, let me know. Please do not Google it. Okay, so go to the folder, and these are the notebooks. Okay, so I'm seeing the charts, but I couldn't get the right answer. Okay, so this library is very interesting, guys. So till my notebook is opening, the name of a library is ELI5, which says that explain like I am 5. Explain like I am 5. So if you are having machine learning and you are explaining it to the kid, okay, and that kid will ask you, hey, this is my trained model and how it is trained, and you want to explain the behavior of machine learning model to a kid of age 5, how you will explain it? ELI5, explain like I am 5. Okay, and that's why this library, and so beautiful library. Hope you are ready with me. Just give me yes. I need most of the people to be at this page when we run it together. If you are ready, let's do it together. Just give me some kind of a feedback. Yes, yes, yes. Fantastic. People who are not ready with the notebooks and who are not ready with installation, that's fine. I'm not showing any rocket science. You will be having these notebooks, and you will be getting the recordings of the session also. So just don't worry. If the things are not ready with you, just sit back and enjoy, and just get confirmation about that you have learned is the same or not. Okay. Okay, so first thing that we have to do is click on a notebook called Global Explanations. Great. If you see something is already executed, click on a button, cell, all output, and clear. Okay, so the library that I was talking about is called as an ELI5. So this library you will need to generate very easy the simple classifications. So those who do not have this library installed, the single cell will install that library for you. So what I'm doing is pip installed ELI5. So when I run it, if it is already there with you, system will tell that a library is installed, or if it is not, then it will get installed for you. Okay, so I'll just wait for a minute. So here you will see that if ELIFI is already installed, it will say that requirement already satisfied. If it is not there, then it will get installed for you. Okay, pip install ELIFI. Cool. And just don't worry, if you get some kind of an errors, you can send me that offline and we can work out together. These There could be some uh, dependency error at the time of installation also, but that is fine. Okay, so ideally when you write this pip install ELIFI, it's not a heavy duty library. It will get installed very easily. So now you have this library ELIFI. Okay, let's see how to use it. So what I'm doing is, this is a very standard import. What I'm taking pandas for reading the data, numpy, matplotlib for showing some graph, cbon on the top of matplotlib for generation of some visualizations. And for the explanation, you all agree that I'm taking a random forest. You can play with this by using XGBoost and some other classifiers as well. But random forest, everybody agreed that we use random forest a lot and we know that it's not explainable. So let's see how to generate explanations for that. SNS style, I'm just, designing some of the visualization settings. And there is a folder in XAI library. The folder, there's file called data. So I have shared this file with you, the CSV file. So when you go there and see panda.read CSV, it will read the file. And this is how the simple data looks like for you. So for sake of explanation, I am taking this data for predicting whether person will have a diabetes or not. So this data is called as PIMA Indian data set, which has a column like pregnancies, glucose levels, blood pressure, skin thickness, insulin, body mass index, diabetes pedigree function, and age. And then you have a very nice column called outcome. This outcome 1 indicates that person has a diabetes, and 0 indicates that person is not having a diabetes, right? So please pardon me, I'm not doing any kind of very interesting feature engineering stuff, but that's your job and you can do it on your data. I'm just taking data as it is and saying that my target column is an outcome, and then I'm just using train test split, and splitting size is 0.2, and this is how I'm generating my training and testing data. For sake of simplicity, I'm saying that I'm using random forest classifier. Number of estimators 10, you can change that, and the max depth is 5. So again, I'm saying I'm not doing any sophisticated hyperparameter tuning here. This is just a sample model that I have trained. So when I train this model, it's saying that I fit the model on X train, Y train, and I'm scoring it on X test, Y test. So what is my test accuracy? Test accuracy is 77, which is pretty decent accuracy without doing any feature engineering or any parameter tuning. So let's say I'm very much happy with this 77% accurate model. But as I said, this is a black box model for me and I cannot use it like that. So if I want to generate explanation for this kind of a model, I will be using a library called ELIFI. So this ELIFI library, what it does is I need to tell them what are my features. So what are the features? Pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, and age. These are my features. And my classes are non-diabetic and diabetic, right? So this is a very interesting and a very elegant function called ELIFI.explain weights for a given model. Now, this model could be any model that you train. This method is model agnostic. It could be logistic regression, it could be SVM, it could be a naive Bayes, it could be random forest, it could be KNN. Whatever the classifier that you have, you need to pass that and the features names to it. That's it. And then it will generate the visualizations for you. Okay, I forgot to run this. Import ELIFI and then run it. See this? This is how the feature important plot looks like. So what does graph? So that's why you will understand that this method is called as a global explanation method. This method is explaining you at a global level that overall My machine learning model is giving a very high importance to a column called glucose. The second importance is given to a column called age. And the third importance is given to a column called BMI. And now, when you show this to a medical expert, okay, he will definitely say, yes, obviously, if you want to predict, if you want to predict whether the person is having diabetes or not, you have to monitor the glucose first. Also, from my knowledge, I know that age also plays an important role. The chances of having diabetes, I'm talking about type 2 diabetes, is very less compared in children. So age is very important factor. And the third important factor could be a body mass index. Yes, it is proven that the people who are uh, obese, they have a chances of having diabetes are more. So he will tell you that after looking at this, hey, go ahead with this model. I'm pretty happy the way in which features are giving what level of expectations. Are you with me? So that's why this is called as ELI5. So a 5-year-old kid, you can say that, hey, if I want to predict a person is having diabetes or not, I will first check what is the sugar level, what is his age, what is an BMI, and then other factors. But these three factors are of a prime importance. Okay. And this is an explanation that we are generated for a random forest model, which is not inherently explainable. Now I'll take a pause here. I will ask the question to audience. Can anybody from you tell me what is the limitation of this kind of a graph? What information is missing and why I cannot stop at this level for generating explanations? Can you tell me um, what is the what is missing in this graph? Any ideas? Yes, you can also so there is a question that can you explain neural network? Yes, you can explain neural network by this also. So Keras has a method for generating this for ELIFA, but you just have to use that utility extra. You can still generate explanation for neural networks like this feature importance. Okay, so my question to the audience is, can anybody tell me what is missing in this graph, or you're happy with only this explanations? What is missing?
So I wanted to say that it doesn't describe basically a change in glucose, how it impacts the outcome.
Yes, that's a perfectly right analysis.
It is
Relation
like
between,
correlation is given, but not exactly how it will impact.
okay, okay, cool. Yeah, I'm getting relations between the features. That is also correct. So at a very simplistic level, somebody explain, this model is telling me that glucose has a highest impact on the decisions. But is it telling you that increasing the glucose increases the chances of having diabetes? Whether glucose has positive impact or negative impact? What is the range in which glucose has already actually start impacting? Just saying that glucose is important is not enough. You need to tell me what levels of glucose has what kind of an effect. That is first. Second is, you also need to tell me that whether the impact of a glucose is positive or negative, right? So these all things are missing in this kind of a graph, right? Let me check chat if somebody else has some other opinions. Causal versus correlation is a very is a altogether different ball game. We will have a discussion on this sometime, but it could be a correlation as well. Causality, nobody can claim that that's a causality that it has learned. Let's see. Okay, so two things. One is what values of glucose and what is the corresponding impact of that values of glucose, and second is whether glucose is having positive impact or negative impact, right? Now for diabetes you can easily figure out, but for other models it may not be that clear. right? So for that reason, we have another explanation method, and that explanation method is called as a partial dependence plot. Okay, and let me add a screen so that I can draw some nice graphs. Okay, partial dependency graph. So what is it? Okay, so partial dependency graph is a method in which what you do is you take one feature. Okay, so this is your column, say x1. You have chosen a feature x1. Okay, suppose glucose. Okay, then what could be the different values of a glucose? So a glucose could be 0. Person who is dead, glucose could be 0. A person is having a very high diabetes, maybe 300, 400, high diabetic level. 400 is a glucose. I have seen people having more than that, but sake of explanation, I'm taking that 400. Now, and this is your probability of outcome. So how this partial dependency plot does is, so from your training data, so this is the training data that I have drawn for you, which has a features like x1, x2, x3. So you have features like x1, x2, and this is your target column y. Okay, so how these partial dependency plots are drawn? You take the first example. Okay, so this will be a feature of your first example, and this is your feature x1, say glucose, right? And you will have other columns also like age and body mass index and diabetes predictive function. So what you do is you keep all other features constant. You keep all other features constant for this one sample, and you change the value of x1 from lowest value, that is 0, to highest value, that is 400. And for every value of x1, keeping all other constant, you actually see what is the outcome of your classifier. So you will increase the glucose and you'll say that, hey, glucose is low, and all of a sudden there is a sharp. Are you getting me? So for one particular sample, you keep all columns constant, and for that particular value, you change it from 0 to highest value, and for every value, you note down what is the outcome of your classifier. So here is 1, here is 0. So when glucose is 0, 0, 100, 90, it has no effect. And now when everything is constant, and if you're just increasing glucose, you'll say that you will start getting sharp one after some time. It is flatten after that. Are you getting me? Are you with me? So for one sample, you have a one graph. So if there are 200 rows in your data, 200 is a very small number. Suppose you have 2000 samples. For every one sample, you will keep all other column constant. And for the glucose only, you will have another graph. You will have another graph. You will have another graph. You'll have another graph. You'll have another graph. So likewise, you will have 2000 lines if there are 2000 samples in there. And then from all that, you will calculate a average of it. And that plot is called as a partial dependent plot. Why I'm calling it as a partial dependency? Because I'm keeping all other column constant and only seeing the effect of changing this value from minimum to maximum, not for one, but for all training samples. And that's why this graph is called as a partial dependent graph, partial dependency graph. And this is how that graph looks like. Partial dependence plot. So the blue one that you are seeing is the average one. If I have with a program, if I have drawn all the 2000, you will not see anything. But ideally, I have explained you in this method that how that blue line is drawn, right? So what you do, you change the value of a glucose from very negative value to high value. For every sample, you do it, and then it's an average of it. So here you see the change in probability, and here you see the glucose. So how to interpret this partial dependence plot? You see that when all other factors are kept constant, And if you just change the value of a sugar, you will see that after 120, 140, 160, if you have a values of a sugar in a range of 160 to 180, we don't care what other values are. My model will predict that person has a diabetes because it's already has reached 0.6, right? So beyond 160, if you are having glucose, it's already 0.6. What it says that I don't care what your other features are. If sugar is in this range, boy, I'm just gonna predict that person has a diabetes. No matter what is your age, no matter what is your gender, no matter what is diabetes pedigree function. This is how my model is behaving. Are you with me? I'm not saying this could be a medical correct or not, but I'm generating explanation for a factor called glucose that this is how my model is behaving. Now you will show this to a medical doctor. And if your medical doctor says, I'm okay to deploy this kind of model, this is perfectly fine, this is how it should be, then only you will go and deploy this. And that's why now, can you compare from that previous slide? Don't you think that this slide is adding more effect? It is giving you more information compared to a simple feature importance plot. So if you increase the complexity, you'll see that yes, it is definitely adding a value. Now I can see that how my glucose is affecting my decision. Are you with me? Now, if you have agreed to this and if you understood this, yes, it is a value. Let me take back to the notebooks and let me explain you that how to generate in this into the Python. Okay, so let's go back to IPython notebooks. Partial dependency plot. So your scikit-learn has already, if you have a latest version of scikit-learn, you have already a partial dependence plot. And if your model is not a scikit-learn model, there are other libraries available for partial dependency plot. So don't make, don't feel that, this method is dependent for the scikit-learn kind of a models. Just to get started and for simplicity, I'm using the function from scikit-learn. But there are other Python libraries, independent libraries, which will allow you to generate partial dependency plot for any algorithm that you are using. Okay. So what to do it? It's very simple. From scikit-learn.inspection, import partial dependence. And what I'm doing is generate a partial dependence plot for a model. So this model is anything that you have used. Again, I said this method is model agnostic method. So I don't care what is in the back. I'll pass my all training sample. You can pass your test samples also. And for this glucose, so when I run this particular line of code, I'll get this graph. And similar graph, instead of glucose, you can generate it for other aspect, like for age, right? So for age, if you want to see that how that graph look like, for every column that you use, you can see that this is an effect of an age. Now you can see that so you must have heard that, right? In the range of 45 to or 50 to 60, now I'm in 50s, late 50s, now I'm getting diabetic. That really you can see this from the graph. I really liked it. So this is how you are figuring out how your model is learned. I hope this is the starting point. So normally when people use this explainability technique, very important thing is, okay, let me know what are the important features. So people draw this graph and then pick one by one feature. And for that one feature, they generate the dependency plots. Are you with me? Now, if you have understood this, can anybody from you tell me that what could be the limitation of this? What could be the limitations of this partial dependency plot? Anyone? First of all, have you understood how partial dependency plots are generated and the value of them? Have you understood? Give me a feedback. Okay, I got a lot of yes. So most of you have understood. Okay, now if you have understood, then there is a follow-up question. Then can you tell me what could be the limitation of this? And obviously, if you tell me the limitation, then I'll definitely ask you how to overcome this. Okay, so limitations is keeping constant except one. Yes, you got it correct. And that's the name suggests, partial dependent. But in reality, you will see that, hey, here you are assuming that all my columns are independent of each other, and you are just changing one column and keeping all other constant, right? But that's not in reality happens. There could be relationship between the values. So there is assumption that we are making. Yes, this is an assumption, but that's a limitation, right? Because you want to have that simplicity. But in reality, we know that they are not. So can you help me to improvise this partial dependence plot? Can somebody help me to improvise this? This is very open-ended, right? So we have learned this, we liked it, but we are saying that, it's not complete. So help me understand to propose a new method where we can um, improvise it. So another way of improvising it could be any suggestions before I tell you? How can I dependency on other feature is missing? Yes, so everybody understood this now. Now you need to help me. How can I solve this dependency? How can I improve this visualization? How can I add more value to it? Anyone? How can we improve this? Bunch of a feature vary on minimum to max and other. Yeah, this is the good thing. So rather than bunch, how can I improvise it? See guys, this is how I used to do before. This is my features. This is my x1. This is my x2. This is my x3. This is my x4. And this is my xn. So what I used to do is I used to keep x1 constant and keeping x1 variable and keeping all things are variable, right? So I got a 1D plot like this, only effect of x1, right? The simple extension of this method could be, instead of x1, what I'll do is I will keep x1 and x2 changing and keep rest of constant, right? So x1 and x2 both are changing. So you will try all values of x1 against all values of x2. What you will get? You will get a 3D graph like this, a heat map, right? So here is your x1, here is your x2, and the third dimension could be a heat map, and red area indicates increase in probability. I hope you got what I'm trying to do here. So as you change x2 correspond to x1 for a particular combination, or x2 and x2, what is an effect on probability? So you can extend this partial dependency plot from 1D to 2D, right? But what if you want to do to 3D, 4D, 5D? After that, it becomes so difficult for you that you will not be able to visualize it. But we have to live with this limitation, and maybe there is an open-ended now. I'm not saying everything is solved by now, but we are here, and it's an open-ended problem for you. How can you come up with a technique which has a better visualization? For now, I don't know which one can do this, but I would like to open this to the audience that this is a problem, and you can work on it and propose a better way for visualizations, right? I need to keep eye on the clock, and I need to keep on moving. I hope you like this, and let's move forward for the next type of explanations that we're gonna generate, and that is called as a local explanations. Local explanations. So in a local explanation, as I told you, so far, whatever explanations that we have seen, those are the data set level, at a global level. This is how your model is behaved. But here onwards, what I will be doing, I'll give you one sample, and for that particular sample, you will have to predict that why my model is saying that it is predicting 1 or it is predicting 0. So interpretable machine learning models, let's get started. Very simple. Suppose if we are designing a classification model, which is having x1 and x2 here, and there is a column asset and annual impairment. Suppose if you want to predict whether a loan could be repaid or not, this looks a very simple model. You can draw a straight line. So it could be a logistic regression, and you can say that if the data point is lying on or above the line, I'll call it as a positive, that person will repay. And if it is lying below the line, I'll say that it's not gonna repay. So very easy, linear decision boundary, logistic regression. You can justify the decision. When you say it will repay, you can say that his assets are more, his income is more, and then you can justify this. Okay. You can still say that, do I have to restrict to a linear boundary? Not really. We already made an explanation for non-linear classification. I can have a decision tree, and suppose there is a model cat, should I buy a new car? And then you can make a decision saying that if a mileage is less than 25 and if it's less than this, I can decide whether to buy or not to buy. I can still make a justification for this kind of a model, and I can still justify locally also. For example, this is my sample. What is an outcome of this sample? The outcome of this sample is no. Now, can you justify no? You can say, hey, your mileage is more and your age is something here, and that's why I'm saying you not to buy a car. Are you with me? So I can justify the decisions locally also, because these models are inherently interpretable models. So there is no problem with logistic regression and decision tree for generating local explanations as well. The things will get complicated when you have something like this. Now, there are not, so the complexity is, so this is your x1 and x2, and this is the learned function. Look how non-linear this function is. The boundary is very complex, right? And you have a lot of features also. How you can justify this? Now you cannot use a logistic regression or simple decision trees for this. Okay, it is very difficult for you to access. So you have to use some kernel SVM or neural network or these kind of models, right? Now the question is, can you generate a local explanation? Local explanation means you will have to justify the decision made for a single instance. So here, this is my instance, this is my data point, and that is lying in my red region, that is a positive. So I'm making a positive prediction for this particular point, which is on this boundary. I'm calling it as a positive instance. Will you be able to justify why I'm calling it as a positive? That's the question. Are you with me? Now that could be very difficult to justify for a one particular instance, whether it is a positive or it's a negative, right? So what I'll have to do is, I will zoom down. So let's go down. This is the data point. This is a data point, and data point is here, and the prediction is positive. What I'll do is I'll apply one more level of zoom to it. So this is like a 9x zoom. And here I can see that this is my data point and my prediction is positive. Now I want to justify this. Okay. So what is the trick that is used here? So very interesting paper that got published. And what they say is that when you zoom it to a level, to such a high zoom level, for that particular reason, you can still draw a straight line to differentiate the positive and negative examples here. So these are the negative examples and these are the positive examples. Okay. So there is a method, and this method is called as a local interpretable model agnostic explanations line. Local. So what they're saying that my model at a global level, it's very difficult for me to generate explanations, but I can zoom in to a level where I can design a simple linear classifier for which I can generate an explanation. So again, you will see that, hey, Bhushan, you are not solving the inherent problem, but I'm saying that these all are the different bypasses that people have proposed. That this whole model is not interpretable because it's highly non-linear model. But what I will do is I will zoom out to where your instance is. I will go to that level and I can say that this region, I can generate a linear classifier and I can generate explanations for that part of your model. And that's why the name of this method is called as a local interpretable model agnostic explanations. This paper got published in 2016 and kind of a legendary paper which starts all this journey of explainability and need of XAI. So it's like a path breaking philosophy that they propose. And the paper was published saying that why should I trust you? Why should I trust you? And say that we will explain the black box model. And again, the method is model agnostic. So I don't care what model that you use in the past. Locally, I will make it interpretable. Okay. LIME stands for local interpretable model agnostic explanations. So what this method tells you like this. Now, please understand this. What is saying that suppose this is your highly nonlinear boundary that you want to explain. So this is a highly nonlinear boundary that you want to explain. This is a point that you want to generate explanations for that point. Okay. So what you're saying that sample the points around X. So this is the point X, which we want to generate explanations for. Now you have to sample the points around the X. So what are the points sampled? So these are the points which are around the X. Okay, these are the points which are around X. Sampling, random sampling. Now use the original complex model, the model that you use for that to predict the labels. Now take all these samples around this, okay, and use the original classifier that you used to make a predictions of this. So for this, the nearing model, my model is calling this a positive, 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 negative, negative, negative. So around this, right? Now, very important step 3 is weigh the samples according to the distance from X. So this is my point. If you are close to me, I'll give you high weightage. If you are close to me, I'll give you high weightage. Close to me, I'll give you high weightage. If you are close to me, high weight. So from the surrounding, the neighbors which are close are weighted positive. And very important, train a simple model on the weighted samples. So that's why this technique it's called as a surrogate model technique. So you have the original model which has learned this very complex functions of producing positives and negative samples. But this is a complex high non-linear model. Maybe a neural network has learned such a complex functions. And I know I cannot generate explanations for that. But what I will do is I will generate a local, another model on this samples. And that's why this model is called as a local surrogate model, which is trained only on this part. So this looks like a simple logistic regression, isn't it? Here are the positive samples. Here are the positive samples. Here are the negative samples. This is the decision boundary. Now this local boundary is linear. So train a simple model. This simple model we will choose inherently explainable model like logistic regression or decision trees for which you can justify the decision. And then use the simple model to explain your decision. Isn't it great? Right? So I will repeat this again. No matter. So let me explain you with this. Suppose you want to predict whether my this point is a negative. How can I say that? Okay, this is my negative point. I will sample all the points around it. Here, 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 all the points around it. Then I will use my original classifier to make predictions. Right? Then I'll find the closest and give high weightage for them which are closest to this. Then on that highly weighted, I will design a linear classifier. And I will use this surrogate model to generate local explanation for a point X. And by this way, I solved the problem saying that, hey, your overall model could be highly complex, non-linear, but at a local level, I can still generate explanations for it. Are you with me? I'll take a pause here. Let me know if there are any confusions. Isn't it amazing? That's why it's called, I don't care what model you have. Model agnostic explanations. Local interpretable. This is a local model. And the small model that I will use will be highly interpretable. Isn't it great? I really love this. This is the first thing which got proposed and got a lot of popularity. I hope everyone understood how Lime works. Any questions? Amazing. Cool. I'll quickly show you the example. Now, I'll not spend time on the notebooks because I want to have a very interesting discussion on this. So hope you liked it. And the way Lime was proposed similarly, um, so let me go back to the notebooks. So in the notebooks, you have another notebook called Lime. So click on that. Again, you will have to use pip install Lime. Okay, I'll just run a little bit faster. Pip install Lime, and then you take the data, then you train the model as a random forest classifier, and then you predict the model, and this is how the interpretations are generated. Now, these are the local interpretation. For one particular data point, my model is predicting is as a 0.6 like a positive. And why it is saying it positive? Because my glucose are more than 141. My glucose is 177, and you know that glucose has a high importance, right? So my model is predicting that person will have a high diabetes because one of its very important feature called glucose is having value much more. So 177 is a very high glucose value. And what I learned is, and how I'm explaining this, see, your glucose is more than 141, and that contributed towards positive decision. That person will have a diabetes, right? Now, though age of a person is 24, age of a person is 21, which is less than 24. So this age actually contributed towards saying that no, age is small. So this person is younger. So chances of diabetes could be less. This is how your age is factoring. But look at the body mass index. Body mass index is 34, which is between 32 and 36. So body mass index also contributed positively. So out of your top three features, your glucose is very high, your BMI is very high, though your age is small, my model will predict that person, hey, you are having high chances of diabetes. Are you getting me? So don't you think that this is much better than what we saw? So I'm not, so it would be an apple to orange comparison if I say that this is better than global, but what I'm saying is it's also important. So at a local level, you can generate an explanation for a single person. For that case, you can tell me, hey, you are having a diabetes, you will not have a diabetes, kind of stuff. Are you with me? Isn't it exciting? Right? So if you like it, you play with this notebook on your data, replace the diabetic data with your own data, and generate beautiful local explanation and start using this, okay, in your day-to-day work. I'll switch back to my slides now. So there is a toolbox called AI Explainability 360 by IBM. It's an open source toolbox. It has a very good APIs that you can use. Uh, there is another notebook that I have shared with you that is called as Interpret ML from Microsoft. So there is a library called Interpret ML. If you have a time, just pip install Interpret ML, and this will give you amazing dashboards. Okay, so let me run it all for you. It will, it's like a combining all the methods that we have learned into a single dashboard. So you will get a dependency plot, you will get a line, you will get you will get feature importance plot, everything with a single dashboard by using this library. Again, it's not a rocket science. I have given you a sample notebook. I would request you to use it on your data set. So its visualizations are amazing. Okay. You can choose that what features I want to use, and then you will get nice explanations coming back. Look at this. These are the feature importance plot. These are like partial dependency plot, and you can do this. Okay. I'm really sorry. I need to learn fast because I want to discuss some very interesting features with you. Okay. So play with this. Interpret ML. You can install locally and quickly use it. And as I told you on slides, there is another a nice toolbox called AI 360. These all methods that I'm talking about, you can get nice Python APIs there. Okay. Now we have 6 minutes in hand, and I want to discuss with you What could be the challenges of using this? Can anybody from this room? So far, I was discussing with you that, hey, you should explain your models. Explainability is very important. Nobody can buy your models if they are not explainable, blah, blah, blah. Lot of importance about explainability, right? This is a time. Can anybody tell me what could be the limitations of explainability, or why somebody should be very careful in order to generate explanations of their models? Quickly.
So one challenge is that uh, the flaws of our model gets exposed, like that's
That is
snow.
good. You should not hide your models. Okay. So if there are flaws, let it be openly discussed. Okay. I'm really sorry because I'm having limitation of time, but we can have discussions. I still have 5 minutes. Look at this. Fooling Lime and Chap. Why should I trust you? Is the original paper published by Lime. Now people are asking, why should I trust your explanations? Right? Because your explanations can be fooled. Okay, so there are attacks on the models, and we have a dedicated session in this key. How can you avoid attacks on your AI systems under secure AI, that I'm going to cover maybe after a few courses. But here is fooling the Lime and Shap. Okay, what they say is that when you perturb, now I'm very sorry, we have a time limitation, but the author of this paper, he has its own YouTube video where he has explained this paper nicely. Okay, so I'll not repeat it. I would highly recommend you note down the name of this paper. And what he said, now this is from his paper only. These are the points which are the blue ones. So this is a PCA of a high dimensional into two dimensional. Blue points are the points which are from your data sets, the original points. And the red ones are the sample points that you took around the data. So, I explain you here while generating an explanation that this is your point, and you randomly sample points around it. Yes or no? Right? So these are the random points around your point, right? So what he's saying that when I took the sample point around it, a line samples, and when I saw their two-dimensional visualization, the blue ones are my original ones, and the red ones are the sample ones, and they are not going close to the blue ones, the samples around the original ones, right? Now he says that, what if I train a classifier in such a way? Now guys, please, with a high concentration, just try to look at. This is the boundary that I have learned, and these are the samples here, right? Which my Lime will pick. What if I train my classifier, which is highly resist on my original data points, but which would be very good around this boundary? So what he says that I will design two models, one on my original data points, which will be highly resist, high biased on the race. I can simply put, if the race is this, then predict one, else zero. So if that much biased data, that is the model which is in this boundary. But around these data points, I will have a fair model, right? So what your Lime will do, because Lime uses the same model for the around data points to make a prediction, you can completely fool the explanation because your model. So what he has done is, in machine learning, while training the data, you are not careful about what is my data distribution, right? Because you never know that Lime would be used in future. So your model is trained only on these points, but it takes surrounding points to make decisions for generating local boundary here. So he said that I will design two models. One is a very biased models on original data, and a unbiased model around it. That's how I train my classifier. But so when you take help of the surrounding points, to design this local classifier, you would be completely fooled. Okay, I'm very sorry if I couldn't explain you in depth, but again, I say there is a YouTube video for the author. Have a look at it, and he has amazing explanations on how he fooled the Lime explanations. Okay, so explanations can be fooled. So this is my bias classifier, which is giving only importance to one feature by using some advisable attacks of other features. The explanations are not saying that your model is biased, but really the model was biased. Okay, so lime and chap explanations can be fooled. Okay, this is limitation. Second limitation is on privacy risk of model explanation. So can adversary leverage the model explanation to infer the private information? So if you generate explanations, from your explanations, I can figure out what could be your training data. Because I know from explanation that you put importance to which features. So there are approaches where people are saying that I can reconstruct your model from your explanations. So model reconstruction from model explanations is another paper that is published. So have a look at these papers, and that's why there is a you know, there is a paper which has a lot of arguments coming that now this paper was published in Nature saying that stop explaining black box models for high stakes of decision and rather than use interpretable models, because if you start generating explanation, people will people will fool the explanation, people will learn your functions, and there are a lot of questions being asked saying that how can I trust your explanations, because in order to explain one model you are training another model on the top of it. Now who can give you a guarantee that the smaller model that you have trained will be accurate, right? So to solve one problem you are creating another problem. So now I have kept all the things in front of you. So we learned that there is a trade-off between interpretability and performance, and we learned that how XAI can be used, and we discussed that any black box model can be explained by techniques like lime, dependency plots and all that stuff. But the question in front of you is, hey, if you use a highly interpretable model, then there are privacy risks. Are you with me? So if you're saying that, hey, it is highly interpretable, then I can say I can hack it. Okay. So I would leave it to you, and lot of open-ended research problems in front of you. I hope you like the sessions. And as I said, it's the latest thing. A lot of open issues are there, and you can pick one and pursue your research. Okay. I will stop here. I hope you liked it, and happy to get your feedbacks. Thank you so much. Over to you, Prachi.
Yeah, thank you so much, Dr. Bhushan. It was a very nice session, lot of insights through it. And participants, if you have any questions, please ask. Um, so we have a lot of comments coming in that it was a great session and thank you from people.
Thank you so much.
But apart from that, if you have any questions, please ask people.
And you can send me over email also. I would happy to answer, and
Also, you
see
can
you
write.
see you again on the security and attack session. Yeah.
So next
Thank you.
session will be there. So the next session for the course is on 19th. Um, okay, so on 18th, I will again send a gentle reminder to all of you. Yeah. Hope to see you next in the next session.
Okay.
And
Thank
please
you.
send your please send your questions by email. I will pass it on to Dr. Bhushan. Yeah. Thank you.
Thank you so much.
Thank you so much, everyone.